presence of H2O in the atmosphere is so important to the generation of weather that I want to take a moment to summarize this section of the presentation and draw out some of the main points. Water is a small percentage of the makeup of the atmosphere, between almost 0 and 4%, but it's the only gas in the atmosphere that at normal atmospheric temperatures can exist in all three states of matter: the solid, the liquid, and the gas. As such, it is very influential over weather patterns because when water changes between solid, liquid, or gaseous states, it generates latent heat, sometimes very great amounts of latent heat. Latent heat is an important source of atmospheric energy, especially for storms and hazardous weather. In fact, in your severe weather flying book, Dennis Newton, the author, talks on page 1, in fact, when you look at any sort of weather chart, ask yourself where the water is. What are the dew points? Are the winds coming from dry land or from a source of moisture? He says water is the enemy. Why is that? Well, let's talk a little bit about water or H2O changing states and the generation of latent heat that results from that. As H2O changes from the solid to the liquid and then to the gaseous states. So let's talk about warming of H2O first. So it goes from the frozen state to the liquid state, and then the liquid state warms to the vapor, or to the gaseous state. When that happens, heat energy must be added. Think of ice melting or water evaporating. You're adding heat. Heat energy is taken then from the atmosphere to cause the ice to melt or the liquid to evaporate. Conversely, when H2O goes the other way, from vapor to a liquid and then liquid on down to an ice, it's cooling, therefore releasing latent heat or energy into the atmosphere. Here's a similar diagram to figure 2.3 in your Essentials of Meteorology textbook that you can find on page 32. This diagram is just a little bit different, but it illustrates the changing states of H2O and the resultant heat energy taken or released into the environment. You can follow the blue lines for cooling, and you can follow the red lines for warming. I want you to notice a couple of things in this diagram. First is as H2O cools from water vapor on down to solid water through the liquid state, heat energy is released to the environment. When it cools, heat energy is released to the environment. Conversely, when solid water warms to liquid and then evaporates to water vapor, heat energy is taken from the environment. It's absorbed into the H2O. So heat energy in this case, as it warms, is taken from the environment. Notice one other thing on this chart, that the amount of heat energy released or absorbed varies greatly depending on what state of matter the H2O is going. For example, between freezing and melting, only 80 calories of heat energy is released or absorbed. Compare that to condensation or evaporation, when H2O goes between the liquid states and the vapor states, or the gas. 600 calories, that's per gram, so 600 calories per gram of heat energy is released or absorbed. So between the solids and the liquid, 80 calories per gram of heat energy is released or absorbed. Between liquid and gaseous states, condensation or evaporation, 600 calories of heat energy is released or absorbed. Evaporation and condensation take 7.5 times as much energy as melting or freezing. This concept of latent heat is foundational to our continuing discussion on weather theory. So I wanted to make sure that you have a good understanding of this concept.